So today we're going to talk about covalent compounds and how we name and write their formulas. And then how do we tell the difference between an ionic substance and a covalent substance. So let's quickly review what a covalent bond is. So covalent bonds are formed when two or more anions combine together. So we're going to be two or more nonmetals. So two things from the right side of our periodic table. And in this type of bond, the valence electrons are going to be shared. So if we remember not transition metal, but ionic bonds were formed from the transfer of electrons. So one atom became positive when it lost electrons, one atom became negative when it gained electrons, and that's what held the bond together, that attraction. So covalent compounds or covalent bonds are held together by the sharing of electrons. So here you can see a picture of what that electron cloud would look like. So we have our two molecules, they're coming close together. There's going to be some attraction in that electron cloud holding the bond together between the electrons orbiting each of their atoms and the protons in the center. So most compounds in nature are going to be covalent bonds. This is the most commonly type of compound we'll come across. And a lot of times they're called molecules instead of compounds. Many are used as fuels like ethanol, methanol, propane. Okay, those are all covalent compounds. And many of them form polymers. So a lot of our plastics and papers are made of polymers. So all a polymer is a repeating molecule. So here you can see a polymer in the picture, and each is composed of a repeating unit. So CH2 repeats throughout the whole unit. So poly means many, and monomer means the small molecule. So polymer composed of many small molecules put together. So covalent bonds, when we share our electrons, not all the time are they shared equally. So if something is shared equally, so the electrons they're sharing in the center, like in H2 or Cl2 molecules, the electrons are shared equally, and we say that's non-polar. So it's not an end of a molecule that has a positive or negative side. So it's nonpolar. If the electrons are not shared equally, like in a HCl bond, chlorine likes to hog the electrons more, so you see its cloud is bigger around it than it is around the hydrogen. And this would be a polar molecule. So our chlorine side would have a partial, and we use the symbol, kind of looks like an S, partial negative and partial positive end around our hydrogen. And it's just because the electrons are drawn more towards the chlorine than they are around the hydrogen. And so it makes it a polar molecule. They're still sharing the electrons, but not always as equally. So how do we tell the difference between something that's polar, nonpolar, and ionic? And so we use something called our electronegativity. And you were doing this in your lab the other day. You were finding the difference between the two values. So electronegativity just means the ability of an atom to attract electrons towards it. In that last example, chlorine attracted the electrons more than hydrogen. So chlorine is more electronegative. So if we take the difference between the two atoms' electronegativity values, we can determine whether it's polar or nonpolar. So if our value falls between 0 and 5.5, that would make it a nonpolar molecule, so less than 5.5. If it falls between 5.5, and 1.9, that would make it polar. And if it's greater than if it's 2 or greater, that would make it ionic. And you can see what happens to our electron cloud the stronger the pull is between those atoms. So if nonpolar molecules, both atoms are equally pulling those electrons, so they're evenly distributed. In a polar substance, our more electronegative atom is going to pull the electrons towards it more, the positive one not as much. So our cloud is bigger around the more electronegative atom. And we get a partial negative, partial positive. Then something that is ionic, now the difference is so much greater that the electrons actually get pulled off of one atom and move to another. So that's where we get our negative charge and our positive charge. So the electron clouds literally separate in an ionic substance. So you have this chart on your reference sheet. So it's on the back side. There's electronegativity chart. And then there's the differences there if you don't have those memorized. So 0 to 0.5, nonpolar, 0.5 to 1.9, polar, greater than 2 is ionic. So let's practice using this chart. So let's decide if these atoms are going to form an ionic, polar covalent, or nonpolar covalent bond. So we have O and an I, so iodine and oxygen. So we want to go ahead and look up those two on our chart. So oxygen has a value of 3.5 and iodine has a value of 2.5. So all we're going to do is subtract them. Always take the highest from the lowest. So 3.5 minus 2.5, we get a difference of 1. So that would make our bond fall between the polar covalent. I'm just going to shorten it PC, polar covalent. So let's try the next one. So we have hydrogen and chlorine. If we look those two up, so hydrogen has a value of 2.1, chlorine has a value of 3.0. So always take the highest minus the lowest. And on this one, we get a difference of 0.9. And again, that's going to fall in the polar covalent range, greater than 0.5, but less than 1.9. Let's try the next one. So barium and iodine. So barium has a value of 0.9. Iodine has a value of 2.5. So we're going to take 2.5 minus 0.9. And we get a difference of 1.6, making this, again, polar covalent. Let's try another one. So nitrogen and oxygen. Nitrogen is 3 and oxygen is 3.5. So 3.5 minus 3, we get a difference of 0.5, making it polar covalent again. Must have chosen all the polar covalent ones. And then the last one, arsenic and phosphorus. So arsenic is 2 and phosphorus is 2.1. So 2.1 minus 2, and we get a difference of 0.1, making this nonpolar covalent. So to know the difference between if we have ionic, polar, or nonpolar, we just find the difference in their electronegativities. Okay, last thing we're going to talk about is how do we name and write formulas for covalent things. So they're named and written a little bit differently than ionic. So whenever we're trying to name a covalent compound, we're going to be using our Greek prefixes. So no longer are we worrying about charges because we're not gaining and losing electrons with covalent. That's only ionic. So we have to be able to somehow indicate that there are, for example, 4 bromine. And so we use the prefixes here, Greek prefixes, to represent how many are present. So mono is 1, di is 2, tri is 3, tetra is 4. That's where the game Tetris comes from. So tetra means 4. 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. So we're going to name the first element just like how it appears on the periodic table. And then we're going to add the prefix. The only exception is if there's only one of the first element, we do not use mono. Next, we name the second element, we add the prefix, plus we add the ending IDE. And we always use a prefix for the second element, even if there is one. Let's try this example using our rules here. So C, we know, is carbon, and there's only one of them, so no prefix. So all we're going to write is carbon. Then we're going to name the second element, but we're going to add the prefix. We always have to put a prefix for the second one. So 4 is tetra. And then we're going to name it like we did before, and we're going to add the ending. So bromine becomes bromide. So carbon tetrabromide. So 2 words, carbon and then tetrabromide. Try a couple more. We have NO2. So N would be nitrogen. And then we have 2, so the prefix for 2 is di. And then oxygen, just like before, becomes oxide. So nitrogen dioxide. So you've really been using this naming system and just didn't realize it, right? CO2 gas, carbon dioxide, or carbon monoxide gas, the poisonous gas that you have to be careful of in your houses. Let's try the next one. So N2O, so again, prefix for 2 is di, and then we name the first one just like the periodic table. So dinitrogen. Okay, there's one in the second one. We always have to use a prefix. So mono. We're going to leave that second O off, and then we're going to add oxide. So dinitrogen monoxide. So a lot of times we leave, especially with oxygen, we leave off the A or the O at the end just to make it sound a little better. Let's try number 3. So N2O5. So N2, just like we had up above. So di for 2. Nitrogen, no name change on that one. Then we have 5. So 5 is penta. Because it's going to be oxygen, we're going to leave off that A. So we can have 2 vowels next to one another. And we're going to add the oxide. So dinitrogen pentoxide. Okay, let's try number 4. So we have S, which is sulfur. Remember, no prefix for mono on the first one, so sulfur. And then 6 is hexa. And then fluorine changes to fluoride. My R is a little messed up there. So sulfur hexafluoride. And then lastly, we have P4O10. So the prefix for 4 is tetra. And then it's tetraphosphorus. And then the prefix for 10, deca. We're going to leave off that A because we have oxygen. And then oxygen changes to oxide. So tetraphosphorus decoxide. Okay, let's see if we can go in reverse then. So I gave you the name on these ones, and we need to write the formulas. So we simply just read the formula and rewrite the name. So carbon, C, because there's no prefix, it means there's 1. And then monoxide, so oxygen, and there's just 1 as well. So CO is our formula. No crisscrossing, no charges on these ones. You just simply read the formula, write it. So tetraphosphorus, so phosphorus is P. Tetra means 4, so P4. And then dec, 10. Oxygen, O. And then there are 10 of those. So P4O10. And then lastly, we have nitrogen triiodide. So nitrogen is N, no prefix, so it means there's just 1 and we don't write ones. And then iodide is really iodine. And tri means 3. So Ni3.